Alright guys, we are back with another video, and in this video we want to tackle a problem where we are trying to figure out whether two linked lists do intersect. So imagine that we have two linked lists like this. So we have two, let me zoom in, 2, 3, 5, 7, and we have another linked list. Say for example it's 6, 8, 1, and then 4. Okay, so we want to figure out whether two linked lists do have an intersection, and by that we mean if the two linked lists actually do have any nodes in common. Okay, and when we say if they do have any nodes in common, we actually are referring to their addresses, not their values. Okay, so we could have two linked lists like this. So let me change the color. But these could be at different addresses. Okay, so this address could be different than that address, and the same for the 7s as well. They might have the same value, so if you check for their value, you might find out that they are equal, but we don't care about their values in our case when we are talking about intersection. Okay, so if I want to draw it even more correctly, if I want to draw the two linked lists that do have an intersection, it would look something like this. So this would be this, and we will have another, like 1, 3, and then 5, and then 7. Okay, so what is happening here is that this 5 and this 7 that these two linked lists are referring to, so especially the 5 here, is at the same address as the other node. Okay, as the other linked list that is pointing to. Okay, but this 3 and this 3 are at different addresses in the memory. Okay, so this is what we mean by this being an intersection, but this not being an intersection. So with that out of the way, now let's figure out whether we can do this at all. So these two linked lists do have the same length. Okay, and the most easiest way, like the most basic way that we can think of to figure out whether the two linked lists actually do have an intersection without having this diagram in front of us, just by traversing through the linked list like a blind person, would be to like going through each node one by one. Okay, and then checking if the two linked lists have the same length, and then checking the values at each node with the other linked list to figure out whether there is any matches in the addresses of the nodes. So like at first, for these two linked lists that have the same length, we will check the first two nodes, then we will check the second two nodes, and then the third two nodes, which in this case have the same address. So this would be our intersection. And one cool thing about this is that after we find the first intersection, since by intersection we mean the address in memory, the values at that location and the pointers at that location are the same as well. So what happens is that the linked list that is generated after this intersection node that we are trying to return in this function will be the same in both of our initial linked lists. Okay, so we will reach a point where after a certain node, a specific linked list is repeated in both of our initial linked lists. Okay, so now we know that after we find the first match, then all the consecutive nodes will be a match automatically as well. Okay, so that's that. But what happens if we don't have two linked lists that are the same length? So what happens if I pass in these two linked lists? So we can't do this, right? We can't check it like that. Okay, we can't do this kind of traversal through this linked list. And we don't know the length of this linked list is shorter than the other one beforehand, so that we can make smart decisions and don't check this first node of the longer linked list with anything, and then create a runner in the longer linked list like that, so that we are starting from here in the longer linked list, and we are starting at the beginning of our smaller linked list, and then checking the values like we should. So we don't know the length of the linked list, so we are not able to do this at the moment. What are our options then? So one of our options is to basically traverse through both of these linked lists. So if I traverse through the longer one, okay, eventually I will hit the tail, right? And if I traverse through the smaller one, eventually I will hit the tail there as well. And we can argue that the last node of the two linked lists that have an intersection is always the same, right? Because if they don't point to the same tail, then how are they going to have an intersection in the nodes before it, right? We might even have an intersection that is only one node. So if we didn't have this 7, 5 could be our only intersection node, right? So the tail could show us whether the two linked lists do have an intersection. So we could basically get that value and compare it between the two linked lists and see whether the address of the tails do match. If they match, then we know for sure that there is an intersection between the two linked lists. Okay, so now we know we can return a boolean at this point to for whether the two lists do have an intersection. So with that out of the way as well, now let's see what we can do after we reach the very last node. So one of the things that we can do is to basically have basically, while we were traversing through each of the linked lists, we could also have kept an integer and then counted the length of each of them. So we could say that for the first one, the length was 5, and for the second one, okay, here, the length was 4, right? So we could have that, and then with that, we can easily say that the difference or the delta between the lengths of these two is 1. So we should move the pointer in the longer linked list 1. Like we should start traversing through the longer linked list 1 node ahead of where we usually would start traversing through that list. Okay, so we will start from here instead of there. We will start from 2 instead of 8. So, and then we traverse through the both linked lists once more after we traversed once and figured out whether they do have an intersection at all, and then traverse through everything once more to get to the very first match. So that is one way to do it, and there's nothing wrong with that. This and the only thing that I don't like about this is that it will go to a runtime complexity of 2 times a plus b, right? If a and b are the lengths of each linked list. So that is the only thing that I don't like about it, but I don't think we have that much of a choice neither. So the other thing that comes to my mind is that if we could create a recursive call that called traverse through both linked lists, and then when they both had a node that was pointing to null, like here, it will have a base case and it will evaluate that whether we do have an intersection and whether it's worth resolving the previous calls as well. And then after it grants us the permission to resolve the previous 3 calls, then we would start resolving these. But the issue here is that what happens if the 2 linked lists don't have the same length and don't start at the same place? So at that point, for the recursive calls, we could have a condition. So the first calls would be at these places, the second calls would be at these places, right? And the third call would be here. So here for the linked list that is below, and the next calls would be here, right? And we are reaching the end of this linked list, so we could have a condition for the recursive calls to say if the next node of this linked list is null, then don't traverse through this anymore. Don't call the recursive function for the next node of this linked list anymore. Instead, continue traversing through this linked list only, and then keep this value, and then call the next recursive call with the same value that we had here, right? So then we will keep this, and on the next call we will only move that there, right? We could do that, but the issue that arises there is that what happens when you resolve that last recursive call? And then you will be resolving all the previous calls, but the previous calls were like this. So this is a very last call that you're resolving. The next call that you will be trying to resolve is this one probably. The next one is this one. So you will need to adjust all the previous calls, right? So this isn't what you are trying to. So by resolving, I mean that we want to go back from the end, right? We want to align the ends basically, and then try to go back up from the very end, so that we can figure out what is the last node that had the same address. Okay, so we want to be able to figure that out. We want to go back like this, right? We want to go back like this. We don't want to go back like this, okay, or this. That is not what we're looking for. So if we resolve the very, very last call, which is like this, we don't want the previous calls to be like this. So then we might need to, for when we are trying to resolve things, we might need to have a reference to the lengths or difference in lengths again. and we could have that as a field to our wrapper class. And then what happens is that as soon as we try to resolve everything, we will make adjustments in place. So we will say that, yeah, we were supposed to resolve these, but let's just for now resolve this and this. Let's forget about this, right? Let's go one node ahead because we have this here. Okay. And then this call resolves, and the next call to resolve is this. And then again, we would say, yeah, we know we should resolve this, but like we will override that default call and then try to go one node ahead and then resolve these. And these will result to a match, and we will probably have a variable somewhere called, I don't know, intersection head or something. So I just abbreviated it as int h. And then it was previously assigned to the very last node that we knew that was a match. Now we are overriding its value to be this node. Okay. Then we will continue. I'm control Zing. So I'll have that there. So it is now pointing to that node. And then we continue to go backwards. So after resolving that and that, the next call to resolve would be this and this. Again, we will override that in place. So, and then we will try to resolve for these two nodes, okay, which don't have the same address in memory. So that is that. We could do that. It's definitely doable, and I think it could potentially be faster, even though I'm not sure, because we are doing small traversals inside of each call, right? So the original call is like this. We are doing small traversals on each of the calls. So I don't know if that counts as actually saving on runtime and doing better on runtime, but and it would make our code look much more complicated. I'm willing to give it a try though. So maybe we'll try that one and see how it goes. So yeah, because that would then, if that works, then we know as soon as that we find a mismatch like this here, right? We are about to abort that. So we know that everything from the end is a match until we find something that is a mismatch. And that, I don't know, that could be a good thing, because but it depends. It depends on where the two linked lists do merge with each other. So we could have two linked lists that are like this, right? That have a very short length that they are merged in. And we could have two linked lists that are like this. So we would have to traverse through every single node up until this point, or in this case we would be able to get the head of the intersection in just a single or two traversals from the end. So yeah, I wouldn't count that one as an advantage. Count traversing from the end as an advantage. Yeah, I will give the traversal from the end a shot, because I think that would be more efficient. It might potentially be a little bit more efficient on the runtime, but if that didn't work, then we'll continue with the previous method, which was after we get the delta in length, we will try to traverse from the beginning, but we will have a runner in the longer linked list. Okay, so we are aiming for if we with the first method, we will be able to get to a plus b, which like we can drop the constant and count it as O of a plus b technically. But if traversing, if having a recursive call and traversing from the end counts as saving on runtime, then we will automatically go to O of a plus b and not O of 2a plus b. So that could save us some amount on the runtime. We'll see. So let's jump into the code. Let's create those two linked lists. So I'm going to rename these to something that is more comprehensible. Maybe let me see. So let's keep this one like that. Let's create node 6 to be new linked list node and call it, I don't know, 5. Let's link this with node 6. And let's link this with node 7, which we'll create here, where node 7 is a new linked list node of value 7. Why not? Oops. And yeah, so we have that. Now, what do we want to do? Well, we want to create some initial nodes, right? So I can say var node 8 is a new linked list node with the data of 3. I will wire everything up at the end. Var node A1. Well, let me remove some of these. Okay. Now let me so we have A1 as 3, var node A2 as maybe 4, and I'm going to create node A3 as a new linked list node of 8, and then var node B1 is a new linked list node of maybe 6, or node B2 of linked list node of maybe 4. Okay, so we have these. Now let's wire everything up. So I want to move these to the bottom of these two, and I will move that there. Now I want to point A1 to A2. I want to point A2 to A3. And I want to point A3 to 1. Now I will do the same thing here. B1 would be pointed to B2. And B2 would be pointed to node 1. And now I am going to say that. So yeah, I'm just printing out the nodes here. So print just node A1 and do the same thing for the node B1 here. Then we should see these in our console. Okay, so this is the actual intersection. And yeah. Okay. So now that we have our initial linked lists, let's try working on our function. Let's see if we can implement it in recursive fashion. So as we said, we will have some fields. So I will call this length A, and it will be initialized at 0 for now, and it will be of type byte, and I will create the same thing for length of B, and I will create a public static function, and it will return a linked list node. We are planning to return the head of the intersection there, so it would be 5 in this case. Okay, and in our case would be 1. Okay, now we are planning to return that, and it will be called get intersection. Okay, and it will get 2 linked list nodes, so linked list node of A and linked list node of B, and then inside here we will do a recursive function probably. So let's start with that. So we want to call this function over and over and over again with the next nodes in each of these. Okay, we want to do that, but if a dot next was not null and b dot next was not null, okay, if this condition was true, then do that. And what if that wasn't the case? So else if a dot next was not null and b dot next was null, then call this again, but traverse A, but don't traverse B. And we'll do the same here for B as well. So if that was the case, then don't traverse through A, but do traverse through B. Okay, so these are the 3 conditions. And I'm not writing an else because we don't need to have a condition for when all of these are, like, both of these point to nulls. The only time where we want to have a condition for that is in our base case. So in our base case, it will say if this was null and this was null, then do something. Okay, if both of these were null, then do something. What do we want to do? So we will I would say we will want to have a linked list node and call it intersection head, and then point it to and then if the A, not its data, if A and B were equal, then create that variable and then point it to maybe, let's see, point it to either A or B. Okay, so what's declaration not allowed here? So if I want to declare something, I would have to create that block there. Okay, so we have declared that and we have that now. And we don't need to declare anything if that doesn't evaluate to anything. So if nothing was found there, then just return with null, right? So else return null, I would say. Yeah, I will probably want to return null. Or I would create that here, and then I will assign it to that. What am I doing? And else I will set intersection head to be null. And then we want to return the intersection head for the previous calls. So we have, do we have to return intersection head? Yeah, because we are expecting to get we're expecting to get something of type linked list node at the end of each call. So this is our base case, okay? And then these are all of our consecutive calls. And so at the end of all of these calls, what we want to do is to get the delta, right? So at the start of this, we would want to so when I'm doing each of these calls, I would want to add to the lengths, and I will initialize the lengths as 1, and I want to count them here. So length A++ and length B++. Okay, that's that. And for here, I would want to say to only increment the length of A. Don't touch the length of B. And here I would want to say just increment the length of B and then call the function itself again. So that's that. Now I can for now just return null for the rest of the function, okay, and just call this function and see, or return the intersection head. Okay, so I will probably define intersection head somewhere out here as well. Okay, so this is of type static. Good. So I'm returning intersection head. Now let's call that function so far and see whether we are getting the lengths correctly or whether we are getting the head as we expected to. Like we are getting the head with the same value as we expected to return us. So now what happens is that if I if I run that function, so that was get intersection, and pass it our node A1 and node B2, and call it. After calling it, I would have access to the head here, right? And I should be able to print out the head and print out the head.data and print out the length A and print out the length B. Okay, so let's see which of those we get. So this is the address, this is its value, so it's correct. We are getting the last value. So we were able to stop one of the linked lists from going forward, and then we were able to detect that the both addresses here do match with each other. Okay, we were able to do that. Now the length of the first linked list is 8, so 1 2 3 4 5 6 7 8, which is correct. The second linked list has a length of 1 2 3 4 5 6 and 7. How it wasn't able to detect the length of the second linked list? Length A, length B, length A, length B. Six. For the linkless B, okay, so when we are at this place, we will need to also increment the one that is reaching that final, like if the lengths weren't equal, we will need to increment the one that is shorter by only 1. And this will happen because, yeah, this will always happen. I think I know, I can picture it in my head, but the thing that is happening here is that, like, as soon as we enter this condition, we are not iterating any of the lengths, and the one that is shorter kind of let me see what happens if I get rid of this and then call it with, oops, I'm calling it with B2. Okay, so excuse my lack of attention there. So 8-7, okay, so thank God we didn't change anything. So okay, so we have that now. Now what do we want to do after we reach this point? So we will probably want to first calculate the difference between the lengths. So I'm going to call this one another byte. I'm going to create another byte. I'm going to call it delta length. And I'm going to call math.absolute here and pass the first byte here, so length A, and subtract that from length B, and cast it to type byte. Okay, cool. So this is our delta length. Now, what we want to do with that is to... Now, we are at a place that we want to do the checks between the current A node and the current B node. So we should have an idea of which linked list is shorter, okay? So what I want to do now is to probably say if so if both lengths were equal, so let's worry about that first. So if the length of A was the same as the length of B, okay, then do this. Then say that, let me close this. Say that, like, check for whether A is equal to B, and if they were equal, okay, so if this was the condition here, then assign intersection head to either A or B. Okay, so that is what we want to happen, basically. Okay, so let's now only try this. Let's make these two be the same length. The easier way is by removing A1 and pointing to A2 here. Okay, so if I now do that and run it again. Okay, so it's working. We are returning, so we don't need these links anymore, but we are returning this address, which evaluates to this data in our linked lists, which would be this node, which is the first node that is in our intersection. Okay, so that is working for equal lengths. So we solved it for equal lengths, kind of, and now we are trying to go for a condition where the length of the lists are not equal. Okay, so let's go back up. Let's bring back that node that we deleted. Let's remove these links. Okay, now what happens if the lengths aren't equal? So in that case, else if length A was greater than length B, okay, what should we do in this case? So that means linked list A is longer, which is the case in our example, right? Linked list A is longer. So what will we do now? We will not check for the if A is equal to B and then assign intersection head to A. What we want to do is to assign a certain number of dot nexts here. Okay, so maybe what we should do, so in this case, the length of this is 8, the length of this is 7, the delta would be probably 1, and then we want to attach one dot next to A. Okay, so I would have to calculate that beforehand. So it will be of type linked list node. We will call it runner A, and it will be assigned to, how are we going to do this? Yeah, so I think this is the way to do it. So I'm going to say for by I of 0, I is less than delta, or less than or equal to I is less than, okay, because we are starting from 0. Less than delta length, then I plus plus, and we will want to go to the next node of A. So I'm going to say runner A is a dot next. Would that work? So let me see. Maybe I will assign runner A to just A, and then say runner A goes to the next runner A. Yeah, that seems more correct. And then instead of checking for value of A, we will check for that, and instead of returning the value or the address of A, we will return address of A. So we will essentially want to do the same thing for B here. Okay, so we will have the same steps here. So runner B would be for B, and we will say runner B, and here I will say A, and here runner B, and we won't have dot next here. And yeah, so that would be it. And why is it in all caps? Okay. And what is this? Okay. So there are a lot of conditions here. This is our base case. These are our recursive calls. And this is where we actually start to resolve the previous calls. So we will first calculate the delta length, and then with that we will know which linked list is longer and which one is smaller. And yeah, we will be able to update intersection head with these info. Now let's try to run this again, and we get a 1, which is fantastic. Now what happens if I increase the lengths here? So if I pass now the B2 here, we still get 1, which is good. Now what happens if I change this to be the shorter linked list? So if I now point to A3 here, would this still work? Yep. So, and what happens if I just remove the parts where there is an intersection? What happens if I remove these parts and just remove the pointers here? No, which is what we expected. Unable to read the data. What is this error from? Line 56, which is here. Okay, so it's from our print statement, which is not that big of a deal. So essentially it returned null for the address of the node, and that is perfect. So yeah, I think we have a solution, and it's done with a few fields in our class, and a few recursive calls, and as I said, a base case, and this is where we actually compare the values and update the head. So yeah, let me know what you think about this video, and yeah, I will see you in the next video. Hope you liked it. Bye bye.